Okay, I think I'm doing this. So, chapter 2 is about sequences and series. I don't know if you thought the stuff from last time got a little far out. It was a little far out. We're going to get a little bit back down to earth for a little while. Sequences and series. Today we're going to talk about sequences. So a sequence means just like a list of numbers that goes on forever. So it's an infinite list of numbers, real numbers in this class. And, something like A1, A2, A3, etc. That's what I mean by sequence. And this is typically written, if I want to refer to the whole sequence at once, in our book they write AN with parentheses around it. And the parentheses are kind of important to signal that we're talking about the whole sequence and not just one particular one of the sequence terms. So the individual numbers in the sequence are called terms, and the sequence as a whole is the sequence. All right. Maybe I'll just tell you for now what a series is, although we're not going to talk about series. A series, we're not going to talk right today about series. A series is when we add up or we sum a sequence. And that would be written as the sum n equal 1 to infinity of an. Right? That's called a series. And this is something I hope you talked a little bit about in a calculus class probably. I will just say in parentheses, sometimes this converges, meaning it actually does like add up to something, and sometimes it diverges, meaning either maybe it adds up but sort of becomes infinite, or maybe something else weird happens. All of these things are things that we're going to talk about eventually, but for today we're not going to talk about series. We're going to focus on sequences. Any questions about the terminology so far? I think hopefully these are ideas that you've encountered before. So about sequences. Sequences. That's supposed to say sequences. Can you believe it? Like, for example, here's a sequence. We've actually talked a bit about this one. This has come up as sort of examples. Thinking of that as a set has been an interesting source of examples a few times. That's a sequence. This one I could write. Often it's convenient to write this in terms of a formula. AN. Can anyone give me a formula for term n of that sequence? It is 1 over n. Yeah. So we would write it this way, where the parentheses around it, again, are to indicate that I'm talking about a whole sequence, not just about one specific term in the sequence is equal to an, but all the terms for each n have the form 1 over n. Right. How about, or here's another sequence. This is a very ordinary sequence, just 1, 2, 3, 4. This one you would write an equals n, right? That's another example of a sequence. Or something a little more interesting. That's a sequence, right? I don't want to bother writing out the terms because they're a little complicated, but this is a sequence. And we are going to talk today about some sequences converge and some diverge. Converge basically means when you look at the terms of the sequence and sort of imagine looking out to infinity, keep on following the terms all the way to the right. Do the values actually kind of stabilize at a particular point, or do they not? What do you say about these examples right here, like this one here? Does that one converge, or the opposite of converge is diverge? What do you say?
Does it converge to 0?
It converges to 0, yeah. So this one converges to 0. That is, as you go down the list here, further and further, the values in the sequence, they all get closer and closer to 0. None of them actually equal 0, but they get very close to 0. What about this one here? 1, 2, 3, 4. Does that converge It does not converge. I see them shaking their head. So the word for that is, this one diverges, because those terms in that sequence, they do not get closer and closer to any particular number, right? You might say they go to infinity, but, and that's fine, they do. I know what you mean if you say they go to infinity, but nevertheless, it still doesn't converge. Converge means it actually stabilizes and approaches a particular number, which those ones do not. And what about this one? Anyone have any feelings about this one? Does that converge? You have to imagine as the n gets bigger and bigger, if the n is like super big, does that actually, what do you think?
Actually, I don't know. I think 0.
Yeah, this one does go to 0, although it's considerably less obvious in this case. But this one, would you believe me if I say, it converges to 0. The idea in your mind should be that n, as the n is very, very big, the numerator is going to be fairly big. It's 5 plus n if n is really big. But the denominator is going to be super duper big because it's 2 to the power n. That will be the denominator will be much, much larger than the numerator. And so when you make it go to infinity, it goes to 0. Actually, if you remember your calculus, you may have learned how to show if x is a real number. This actually is plus infinity by L'Hopital's rule. Not plus infinity, it's 0. That's what I said before. If you remember L'Hopital's rule, I don't know if you did L'Hopital's rule, but you would take the derivative on the top and the bottom. On the top, the derivative would just be 1, and on the bottom, the derivative would be 2 to the x times the natural log of 2, and then you do the take the limit again, and you'll get 0 because the top is a constant. But anyway, strange fact, but yeah, sometimes you can actually use calculus to like calculus of real valued functions in order to figure out limits of sequences which don't use real numbers, they use natural numbers. But all right, so there are sequences, they converge and diverge. Actually, all I want to talk about today is what exactly it means to converge, like a real definition of the word converge. When I say, for example, I think the clearest example of all of those is just this one, an equals 1 over n, right? If we were to indicate those on a number line, so here's 0, here's 1, right? These numbers, they look like, here's 1 over 1, here's 1 over 2, here's 1 over 3, 1 over 4. And these numbers, they do like that, right? That's 1/4 there. And when I say they converge to 0, what I mean is these guys here, they get really, really close to 0. All right? And the way we're going to write this, I mean, you can say it converges to 0. We will write like this, lim 1 over n equals 0. Notice when I write the lim in this context, I'm not saying lim as, in calculus you always write limit as x approaches whatever. But if we're only talking about sequences, the n, there's only one thing that the n can approach, right? N can go to infinity. You would never look at a sequence like this, and ask yourself, you know, what happens in this sequence, like when n approaches 5 or something? The values don't approach specific points. The only thing you care about is the limit as the thing goes out to infinity. So we are just going to write lim, and lim always means limit as n goes to infinity when we're talking about a sequence. There's no such thing as going to minus infinity either in a sequence, because the sequence is only infinitely long, like in one direction. No, can't go the other way. All right? The question is, what exactly does it mean? I mean, I already said this, you get really, really close business, but that's not a real definition, right? Remember, that's like the when a mommy and a daddy love each other very much kind of thing. And this is, you know, we're adults here. We can try and talk about what the real, true definition of what it means for this thing to get really, really close to 0. Probably not a surprise. We are going to try to express this using the sort of for all epsilon type language that we've seen can be useful already. So here's the informal statement that I'm going to try to translate into sort of epsilon type language. What I'm trying to say here is as n gets really, really big, can I just say one really? Really big, 1 over n gets really close to 0. All right, I want to try to break this down and sort of translate it into more, technical, meaningful language. Let's look at this part over here. 1 over n gets really close to 0. The way that we're going to describe this is something using a little for all epsilon. I'm going to say for all epsilon greater than 0, 1 over n is less than epsilon. This is how we're going to express the fact that 1 over n may not actually equal 0, but if you choose any number you can think of, any epsilon, real number greater than 0, 1 over n will be less than that, right? So I'm saying here that the 1 over n is going to be less than any number you can imagine. That's sort of the idea there. But this, what I've written just right there, is really, this is only when n is, can I say, big enough, right? I said 1 over n is less than any number you can imagine. Well, it's not true for all the n's, right? Like you can imagine a very small number, 0.001. It's not all of the n's have 1 over n less than that, but when the n is big enough, they will be less than that. So that's so I want to try to phrase this only when the n is big enough. What I mean is there's some kind of minimum threshold, and beyond that point, when the n is bigger than a certain amount, then the 1 over n's will be less than the epsilon. So here's how you got to say this. This is kind of complicated, and you can tell why it took people so long, like historically, to come up with this definition. It wasn't done until like the late 1800s, when people have been talking about sequences for centuries before that. Here's the true definition. It says, for all epsilon greater than 0, there exists some n, a natural number, and I'm going to write as a big N. We're always going to use the same notation here. Anyway, for all epsilon greater than 0, there exists some big N, a natural number, such that if n is greater than this big N, actually our book writes greater or equal, it doesn't really matter, then 1 over n is less than epsilon. All right. So my sort of commentary about this is this right here means if n is big enough. What I mean by big enough, like I said before, is there is some kind of minimum threshold so that if n is bigger than this point, then the value 1 over n will be less than epsilon. And that, what you see inside the red boot there, is expressing exactly this idea of there is some kind of threshold, which we call the big N. And when the little n is bigger than that, then its values for 1 over n will be less than epsilon. All right? So this right here is the definition. Well, almost. This is what it means, just that 1 over n converges to 0. Now, I would like a general definition for what does it mean for a n to converge to some number a. And it's going to look the same as this. Only this one, what I wrote was specifically for 0. We said 1 over n is less than epsilon for any epsilon, so 1 over n is basically becoming 0. The definition in general, I'm going to say the sequence an converges, this is the term I'm defining here, to some number a real number, when it says, I'm going to write basically the same stuff. For all epsilon greater than 0, there exists some threshold big N in the natural numbers, such that if the little n is greater or equal to the big N, then the only part I'm going to change is the very end. because I'm not talking specifically about 1 over n. I'm talking about this sequence, and it converges to the real number a. It's going to look like this. The absolute value an minus a is less than epsilon. So the way to think of that, what this means, your interpretation of that is the distance from an to a is really small. That's your interpretation. Absolute value of the difference between an and a, that you should think of in terms of the number line as the distance from a to an. And what we're saying is that distance is smaller than any number you can think of, right? Which is what it means when you say an is really, really close to a, all right? This is, I don't know if you can if this brings a tear to your eye. There's something kind of beautiful about this definition just because of the ideas that it is meant to express. It's meant to express sort of informal, intuitive ideas about really, really big and really, really small. When it doesn't actually say any of those things, and it doesn't even tell you that the big N is really big and the epsilon is really small, even though it is. I mean, when you think about it, you should imagine the epsilon being really small and the big N being really big. It's a real kind of achievement that people actually came up with this definition. You should, I'll tell you now, you should definitely memorize this definition when it comes to our tests or something, although we're going to use it so often, hopefully you won't have to like sit down and memorize it. But we are going to use this definition all the time. So our remaining, we got, 30 minutes left? I just want to do a bunch of examples showing that this or that sequence does converge to this or that value, all right? Sound exciting? Yeah, so put this definition in a box somewhere. Tell it to your friends and loved ones. They probably won't get it. It's all right. Don't tell it to your friends and loved ones. Let's show. So I'm gonna have to leave the screen with that. So first example, I want to show that. Well, as an example, let's actually show that the limit of 1 over n equals 0. I want to show that this actually satisfies that definition that we just wrote. All right. The definition is quite complicated, which means it will be fairly complicated to show even very simple limits that in a calculus class you wouldn't even really bother getting into the details of. The reason you don't do the details in a calculus class is because we never even told them the definition anyway, so they wouldn't be able to do the details even if they wanted to. But let's show that the limit of 1 over n equals 0. So we have to do a little proof here. Every one of these examples is going to involve a little proof. What we need to do is demonstrate that this definition is satisfied when the sequence looks like 1 over n, and the value of a here, this a, is meant to be the number which the thing is converging to, which in this example will be 0. All right, so I'm going to just start by saying, and there's a very specific format that you will always follow when you're doing these proofs. They are kind of complicated, but there's like a structure that you can kind of hold on to. What we must prove is a statement which begins with for every epsilon. So we need to prove something for every epsilon. And so this proof will always begin by saying, let epsilon greater than 0 be given. I have to prove that something is true for every value of epsilon. So you have to begin the proof by saying, okay, let's just imagine we have some value of epsilon. Epsilon is greater than 0. And what is our job here? We need to find this big N, right? We have to prove that for any epsilon, there is some big N. So I'm going to say, let epsilon greater than 0 be given. We will, the wrong tool. We will find some big N, a natural number, such that this business, if n greater than n, then an minus a is less than epsilon. That is to say, if n greater than or equal to big N, then now over here I'm trying to copy what the definition says right up here. an, it's got to say absolute value. Absolute value, an, of course, in our example is 1 over n. I'm just plugging in what we have here. Minus, what do I use for the a? 0, yeah. A, remember, is the value that it's actually converging to. Less than epsilon, all right? So the epsilon is given. Sometimes, I don't know, if you are feeling, oops. If you're feeling like not saying much, a lot of people don't like writing this. You got to write this in your proof. Let epsilon greater than 0 be given. My good friend and colleague, Professor Mark Demers, I don't know if you know him, his slogan about this is, he says, you can't bring epsilon to the party without introducing him. This is a little introduction. Let epsilon greater than 0 be given. All right, we will find the big N. And now, the next step of your proof is when you just say what the big N is. I'm going to say, let the big N be a natural number with big N greater than 1 over epsilon. Now, why exactly did I say that? There's a bit of mystery right here, which I will try to explain after we finish the rest of the proof. But this step that I circled in green, you have to kind of pick out of nowhere, which makes this is what makes these proofs a little difficult. You have to sort of pull this rabbit out of the hat here. But I'm telling you what the big N is. It is some natural number with n greater than 1 over epsilon. Now, if you imagine epsilon is a very small number, this will make n a very big number, right? Because it's going to be 1 over something very small. So this big N will be pretty big. Anyway, now we must show, we have to show this thing, right? If n is greater than the big N, then I have to show 1 over n minus 0 in absolute values less than epsilon. So I'm going to say, then let little n be greater or equal to big N. And I have to demonstrate that absolute value 1 over n minus 0. Where I'm going with this is, oops, I'm going to write a bunch of stuff here and eventually say it's less than epsilon. This is what we're aiming for, right? We need to show that that thing inside the absolute values is less than epsilon. How do we actually do this? We got to kind of connect this together. I'll take out my squigglies here. That's where I was going, though. Can we do anything to simplify this? What can you do with absolute value 1 over n minus 0? I think you can simplify it, yeah.
Absolute value of 1 over n.
Yeah, minus 0, you don't have to write. It's just absolute value 1 over n. And what's absolute value 1 over n? Yeah, just 1 over n, right? N is a positive number, so the absolute value, you can just get rid of it. Okay. What can we do with that? Now, check it out. I said let n be greater or equal to the big N. This 1 over n then will be less than or equal to 1 over big N. This you got to think correctly about the inequality, but what I did in that step was I made the denominator smaller, right? The little n is bigger than the big N, ironically enough. And so when I turn the 1 over little n into 1 over big N, I made the denominator smaller, which ends up making the fraction bigger, right? Yeah, okay. Can we do anything with 1 over big N? Well, what I have circled in green says n, the big N, is bigger than 1 over epsilon. So I can do the same kind of thing again. This is now less than 1 over epsilon. So this one here was sort of from the red stuff. This one here was from the green stuff, right? Again, I made the denominator smaller, which ends up making the whole number bigger. Anybody like 1 over epsilon? What is that? It is epsilon, yeah. And so actually this is the end of the proof. If you read across the whole thing, what I wrote there. So 1 over n minus 0 is less than, strictly less than epsilon, right? Schön. That's how we do it. This this kind of proof is quite complicated. It takes some getting used to, but like I said, there's a very specific structure which will help you kind of keep your wits about you. Are there any questions at this point about this? We're going to do several more examples. Unfortunately, this was the easy one. 1 over n goes to 0. All right, let's try another one that's a little more interesting. Now, we also need to discuss, how did I get this green thing, n greater than 1 over epsilon? I just came out of nowhere with that. I'll try and sort of, this next example will try and explain that step a little bit better. How about, let's show that lim of n plus 5 over n is, anybody remember something about limits? What do you think the answer is here? You could try and think of this in terms of calculus. X, so x plus 5 over x, what's the limit of that?
1.
Yeah, it's 1. Why is it 1?
Because if n is like a trillion, it's not going to matter if trillion 5 over a trillion.
Yeah. Yeah. Yeah, right. You probably learned some kind of trick about if you have a fraction involving polynomials on the top and the bottom, if they have the same degree, then you do some trick with the ratio of the coefficients in front of the top degree terms. And the coefficients in this one are both 1. So you get 1. All right. Okay, let's see if we can do it. How should we begin? Yeah, just because I told you, you should always begin like this. Let epsilon greater than 0 be given. All right. This time I'm going to try and be a little more introspective about the structure. Let epsilon greater than 0 be given, and then we will find n, a natural number, such that if n greater than or equal to big N, then absolute, what am I going to write over here? I'm screwed now. All right. What should we write here? In the original definition at this point, it said absolute value an minus a. N plus 5 over n, yeah, minus 1. Yeah, what goes here is the value that it converges to. So in this case, it's 1, less than epsilon. All right. This, I'm going to try and talk about the structure. This I'm going to call sort of step 1 of the structure. And this, when you're trying to do this on your own, this part is always easy. All you're doing is saying the let epsilon be given. We're going to find n, and then you just write the definition of convergence. Okay? The next step, step 2, is the part where you just say what the n is. In the previous example, I said let n be some number greater than 1 over epsilon. And that is actually the hard step. You have to figure that out. So step 2, I'm going to do sort of quite a bit of work on the side in an effort to fill in the blank right here. In the previous example, I said let n be greater than 1 over epsilon. But in every example, you're going to have to put something different right there. And what's it going to be? I'm going to do a little sidebar here. Slide it over. How are we going to choose this epsilon? You got to think about what we need in the end is this. Absolute value n plus 5 over n minus 1 to be less than epsilon. The idea here is you should solve this. Solve in the sense of inequalities. It's not an equal sign, but you can still isolate on one side, whatever. Solve this for n. This is your strategy for figuring out where to pull that value out of nowhere in step 2 of your proof. All right? Solve this for n. We should, in order to do that, your principal obstacle usually is going to be the absolute values. The absolute values are a real pain to deal with when you're trying to solve something. But hopefully it won't be such a big deal. I don't know. We'll see. I got n plus 5 over n and absolute value minus 1. Any ideas on, can we simplify that at all? Really, I would like to get rid of the absolute values, but even if not, is there anything we can do to simplify here? What do you think? Yeah, it's 5 over n. How do you get to 5 over n from there? Somehow, anybody see how you can?
N plus 5 minus n over.
Yeah, if you divide or split the fraction up, oops, or if you actually divide by n here, or the way that I think of this is, you can do that, right? That fraction is like that. And now the n over n is 1. It will cancel the minus 1. And what remains is just absolute value 5 over n. And that's positive. So this is just equal to 5 over n. All right? So lucky for us, the thing on the left side, which had an absolute value in it, actually you can simplify to get rid of the absolute value, which is quite helpful. So anyway, now what we need is just 5 over n less than epsilon, right? And I can solve this for n. I would multiply both sides by n first. You have to be careful about the inequalities. It looks like 5 less than epsilon times n. Should I change the direction of the inequality there? No, I should not. I didn't already, so you know I shouldn't. It's because n is positive, and in that step I multiply both sides by n, so you do not change the direction. Okay, and then to solve for n, I would divide by epsilon. So n, it's going to end up saying n is greater than 5 divided by epsilon. All right. And then this is what you're going to use for the big N, all right? All of this work is sort of done on the side. You really, I suppose if you do a lot of these over and over again, you might be able to do this in your head, but I wouldn't recommend trying. You just work it out, solve those inequalities for n. This is what I'm going to do. So back to the real mainstream of the proof here. I'm going to say let n be some natural number greater than 5 over epsilon. And by some kind of magic, the rest of the proof will just work out, provided I did all that work on the side properly. That's step 2. All right, and now step 3 is demonstrating that actually what we want is true. Step 3 always begins with let my little n be greater. Oh, my kid just got a text. Greater than big N. Greater or equal. See, in the third step, you're trying to actually show this little if-then. So when you're showing an if-then, you assume the if part, and then you prove the then part. So I'm going to say let n be greater than or equal to n. Then we have, I'm going to begin by writing the left side of that inequality. And hopefully simplify everything. Eventually, I will show that it's less than epsilon. This is my goal here. Now, since you've already done the work on the sidebar, you can usually use those same steps. So I'm going to do the same simplifying first of all. This is the same as n over n plus 5 over n minus 1, which is the same as just 5 over n, right? Absolute values go away. And now from here we can kind of proceed like in the example we did before. I'm going to say this is now less than or equal than 5 over big N, because I chose the little n to be bigger than the big N. This is the same kind of thing that I did in the previous thing, right? Any idea what I'm going to do next? Also similar to the previous example. Yeah.
The less than 1 over 5 over epsilon?
I think 5 over epsilon. Yeah. Because the 5 in the numerator there. Isn't that cute that it was both 5s? What is that? That is epsilon, yeah. The whole thing just kind of unravels and you end up with epsilon. And so n plus 5 over n minus 1 less than epsilon as desired. All right, and this is the proof. When you're doing these problems, generally this little sidebar is actually what you spend most of your time trying to kind of wrestle with. Provided that you can figure that stuff out, the actual proof that you write in those 3 steps is not so difficult. I like to think of these 3 steps, actually, the structure of the 3 steps is reminiscent to me of of a great film that I once saw. This is a Christopher Nolan film. You know, he did the Batman trilogy and Inception, those kinds. I like those movies. He made a movie about magicians called The Prestige. Any fans of this? Is a good movie. It's quality stuff in my opinion. Hugh Jackman, Christian Bale, David Bowie was in it, playing Nikola Tesla. It's good. You should watch it if you haven't seen it. Anyway, it's about magicians and The Prestige. If you can even watch the trailer and you'll see who's that guy, the British guy. He's in it too. The guy who was Batman's butler. Yeah, Michael Caine. Yeah, he's like Batman's butler again in this movie. And he says, he's explaining the concept. He says, every magic trick has 3 parts. Part 1 is, I gotta stop these. I thought I turned off. Anyway, part 1 is called the pledge. The pledge, this is when the magician shows you an ordinary object. Of course, it's not ordinary, but shows it to you, maybe gives it to you. You can touch it, feel it. All right. The pledge. The magician shows an ordinary object. There's no trick yet, right? This is like step 1 of this proof. You're just saying, here's the epsilon. Here's what I'm going to do. I'm going to find the n that has to satisfy this or that. All right? Part 2 of the magic trick is the turn. This is when the magician makes that ordinary object do something extraordinary. All right? This is what you might be tempted to think this is the whole trick. All right? Something extraordinary. This is what I say is step 2. This is like, in a magic trick, if I have a big hat, I show you the hat. It's a normal hat, right? You say, yeah, it's a normal hat. And then I pull the rabbit out of the hat. That's the turn. This is like step 2 in a proof like this with the epsilons, where you are doing something with these ordinary things that are laid out. And then step 3. Anyone remember the name of step 3? It's the prestige. That's what the movie is called. The prestige is when the magician, after having done something extraordinary with the ordinary object, the magician again produces the ordinary object just as it was at the beginning. And the trick is finally complete. So this is the trick is complete by showing you again the ordinary object just as it was. And that's what step 3 is in this type of proof. Because step 2 is where the magic happens, and in step 3 you are showing everybody that what you said was the magic is truly the magic that you were saying it was, right? You are actually demonstrating that the desired inequality really is true. All right. So these are the 3 steps. If you can remember the structure to these kinds of proofs, hopefully the details will work out nicely every time. I would like for you all to try one. We got 10 minutes left. I want to see if you can do this. So I would like you to mimic as well as possible, structurally, the way that this proof went. See if you can show. So I would like to show that this sequence, 2 plus 1 over square root n. Can anyone tell me what should the limit be? One other downside, or one other thing that makes it hard, is you have to know ahead of time what the answer is before you even start writing this proof, or else your proof definitely will not work if you don't even know what the thing approaches. What do you think? 2, yeah. This 1 over root n part will basically become 0 when the n is really big, and so all that's left should be 2. All right? See if you can do it in our remaining 9 minutes. I will walk around and see what you think. All right, we'll talk about it in a couple minutes. All right.
Yeah, that's great. Can you leave epsilon just as epsilon at this point? Because you're assuming
I just heard like.
it's greater than zero anyway. I mean, would epsilon squared really change it?
It does, yeah. You'll see if you try and do the last part, you need to do that.
All right, let's talk about this. I know not everybody's done. I don't want to steal your thunder here, but so I begin with the first part. All right, so the first part, I saw everybody got this perfectly. Rather than writing if then, you'll see often people just write this big arrow here. This means if n greater than, what? It doesn't even make sense what I wrote there. That should be a big N, not a set of natural numbers. Okay, now your next step needs to say let n be greater than something or other. The work that you do on the side here to simplify this thing, 2 plus 1 over root n minus 2. So first of all, you can just cancel the 2's, and I get 1 over root n, which is positive, so I can forget the absolute values. So this is going to just say 1 over...
Can't root n be positive or negative?
No. That's a good thing to mention. When I say root n, I mean the positive.
Maybe you're right.
Yeah, it's like, this root means like, it's like the square root button on your calculator.
Okay.
It gives you a positive answer. It is a fact that if I say x squared equals 9, solve for x, the correct way to do this is x equals plus or minus the square root of 9, and so x equals plus or minus 3. But when you write that radical sign, it means the positive one.
Okay.
Yeah. Yeah, it's a good thing to be concerned about. Anyway, to solve this for n, we can multiply both sides by root n. I get 1 less than epsilon times root n. And now I can square on both sides. I get 1 less than epsilon squared n, and then divide by epsilon squared. I get 1 over epsilon squared less than n. It is right to be a little concerned about squaring both sides, because that could mess up an inequality if one or the other of the two sides was negative. But in this particular case, we know that both sides are positive, so nothing weird will happen when we square both sides. All right? This is what we're going to use for the n then. So I'm going to say let n be greater than 1 over epsilon squared. All right? And now let's see if we can do, so that was like step 2 of the proof. Let's see if we can do the prestige. So I'm going to say let little n be greater than the big N. Then we have, and we begin with that big absolute value thing. And we're trying to simplify and do inequalities to eventually show this is less than epsilon. I should begin by just doing the same simplifications as before. This is the same as 1 over root n, right? What did you do with this next? Less than or equal to? Yeah, 1 over the square root of the big N, right? Okay, then what? Less than?
1 over 1 divided by radical.
Square root of 1 over e squared.
Yeah, I think, is that what you meant? You are using the fact that n is bigger than 1 over epsilon squared. And so I just replace the big N with 1 over epsilon squared. And then, like a satisfying magic trick, all of this will unravel and you just get epsilon, right? It's kind of satisfying if you do it correctly. The big square root there makes it just 1 over epsilon, which is epsilon. So this stuff, 2 plus 1 over root n minus 2 is less than epsilon, which is what we wanted. All right? It is kind of satisfying, if you don't mind me saying, when it works out nicely. All right, I think that'll do it. We're gonna do some more. We'll do some more examples next time. Oh, I turned the page. Didn't mean to do that.